Hello, Math 2. This is Mrs. Bricky, and we're doing a little bit of a graphing intro today. So here's a function. F of x is equal to 3x plus 2 all over 7. So we are going to evaluate this function for the two x values shown in the table and plot those 2 points. So if I substitute a -3 into this function, f of -3 is equal to 3 times -3 plus 2 all over 7. So you could evaluate that in your calculator if you want, or you could evaluate it in your head if you want. -3 times 3 is -9, plus 2 is -7 over 7, which is -1. So if we plot that point, -3, -1 is right here. And now we're going to evaluate f of 4. That would be 3 times 4 plus 2 all over 7. So again, you could do that in your calculator or in your head, and it's equal to 2. So let's plot the point, 4, 2. So we have 2 points of our function. Are 2 points enough to determine the shape of the graph? And I guess the answer to that is sometimes. It depends. If you know the shape of the function, 2 points might be enough. But if you aren't sure the shape of the graph, then you probably need a few more points to really know what's happening. So if we picked another x value, like if I picked the x value 0, for example, it's not going to be a nice, pretty answer, but if we substitute in 0, we get 2 over 7, which is approximately 0.3, a little bit less than 0.3. So it looks like it goes through this point approximately. And that's not an exact value, but it's a close estimate. Let's see. We could pick another value. Maybe let's pick 8. F of 8 is 3 times 8 plus 2 all over 7. I'm going to just throw that in my calculator to calculate it. And that is 3.7 approximately. So about right there. So maybe you suspected, or maybe you know, that this function is a line. And we could keep substituting more and more values in, and we would end up with a line. All of the points where we evaluated would end up lining up just perfectly with these points as well on that line. So we're going to talk about lines for a minute. Lines have a characteristic called slope, and the slope of the line is a number that describes both the direction and the steepness of the line. Typically in math, we use the letter M to denote slope. So if a line is increasing, like from left to right, it's going up, we would say that that line has a positive slope, or that the M is greater than 0. If the line is going down from left to right, we would say that that's decreasing, and that would have a negative slope where m is less than 0. Two special cases are if a line is horizontal, then the slope is equal to 0, and that's called a constant function. And then if a line is vertical, then the slope is undefined. So those last two are special cases. Slope is a rate of change. It tells you how many units the line rises or falls for each unit that it goes over to the right. So if I go over 1 unit to the right, this line went up 3 units. So we would say that the slope is 3. On this, if I think about moving 1 unit to the right, it actually went down by 2. So we would say that the slope is -2. So slope tells you the rate of change of the line. But sometimes the amount that the amount of units that the line rises or falls is not a whole number, so it can be hard to estimate. So if I think about moving over 1 unit to the right, this line went up less than 1. It went up like part of a unit, but not the whole thing. So in that case, if we're trying to find the slope, we usually look for another nice point on the graph, and we can count how much it went up. So it went up 1 and it went over 3. So we would say the slope is 1/3. And that actually makes sense if you think about that original definition that we talked about. It's going up 1/3 of a unit for every 1 unit it goes over. So then it goes up another third and then up another third. So this is this count, looking for a nice point on the graph, is just a clever way of calculating the rate of change or the slope. So this next one, you can see it's going down 2 and a little bit for every unit it goes over. So if we look for just a nice point on the graph, we can count that it's going down 5 for each 2 units it goes over. If you look at that in decimal form, that's -2.5, and that really makes sense for that original red triangle. It's going down 2.5 over 1, down 2.5 over 1, but it's much easier to count off from the graph and to graph from the -5 over 2. So you have this definition here that can also help you. The slope is equal to the change in y, or the vertical change, divided by the change in x, or the horizontal change. And sometimes teachers will say rise over run. So if your teacher said that in the past, then that might jog your memory about slope. So let's think about slope for these special cases. We talked about slope is how much the line rises or falls for each unit it goes over to the right. So in this example, it's going up 0 over 1. Well, 0 divided by 1 is just 0. A horizontal line has a slope of 0. For this line, let's think about how much it goes up for each unit it goes over. But wait, it doesn't go over. It's going over 0. So we could think of this as that it's going up 1 over 0. Well, 1 divided by 0 is undefined. We can't divide by 0 in math. If you try it in your calculator, you'll get a domain error. So a vertical line has a slope that is undefined. If we know any 2 points on a line, we can determine the line slope without having a nice graph of the line on a grid. So we don't have to be able to count how many it goes up and how many it goes over. We can just think about it. So this line contains the point -5, 1, and 16, 10. So we want to try to figure out the slope. Well, let's think about how much it went up. Well, it started at a height of 1 and went up to a height of 10. So from 1 to 10 means that this went up 9 units. Because it didn't start at 0. If it started at 0, it would have gone up 10, but it started at a height of 1. So our rise, delta y, is 9. And now we just need to know how far over it went. Well, it's starting at a horizontal distance of -5, and it's going all the way over to 16. Whoops, I wrote negative, but I meant 1. So it's from -5 over to 16. Well, that's a distance of 21. So our slope is 9 over 21, which is, let's see if we can reduce that fraction. We've got some factors of 3 in there, so that's 3/7. So our slope is 3/7. So we kind of just thought through the situation with the sketch, but there is a slope formula that you probably will remember once you see it again. You can use this formula anytime you need to calculate the slope through 2 points. So it's just y2 minus y1 over x2 minus x1. So we're just thinking about how far did the function go up, over what horizontal distance did it go over. So I want to find the slope of the line through the point 1, 2, and 13, 8. So I'm going to call this x1, y1, and I'm going to call this x2, y2. It doesn't really matter which one you call which. So y2 minus y1 over x2 minus x1. So you could type that in your calculator just like that if you want, or you could do the subtraction yourself. This is 6 over 12, which reduces to a slope of 1/2. So for our next example, our point is -317 and 2, -13. So I'm going to call this x1, y1, and we'll call this x2, y2. So our slope is -13 minus 17, so that's y2 minus y1 over x2 minus x1. So be careful there with that we're subtracting a -3, so that does end up being adding if you're doing it in your head. So -13 minus 17 is -30, and we're dividing by 5. So it looks like our slope is -6. So these two lines have the same steepness. They have the same slope. If we counted it off, it would be, let's see if I can find a nice point, up 3 over 5, up 3 over 5. Same thing here. If I can find a nice one, up 3 over 5. So they have exactly the same slope, but they're obviously not the same line. So what other attribute could we use to help us distinguish between these two functions? Well, we could use their y-intercepts. The y-intercept is the y value where the function crosses the y-axis. Algebraically, it's the function's value when x equals 0. So here are some linear functions. We want to evaluate each function for x equals 0, and then we're just going to mark where the x-intercept would be. So for our first function, f of 0 would be 2 times 0 plus 51 over 17. And if we divide that in our calculator, we get 3. So this function would go through the point 0, 3. It has a y-intercept of 3. G of 0 is 17 times 0 minus 3 all over 6. So that, if we calculate it, is, if you do it in your calculator, you might get -0.5, or you might get the fraction -1/2. So it has a y-intercept right here at -1/2. And our last function, h of 0, is 1/2 times by 0 minus 5. And if we calculate that, we get -5. So we marked our 3 y-intercepts. So here are two functions. We want to go ahead and graph them by picking values. Now, because they're lines, 2 or 3 values is probably great. In theory, 2 would be good. One of the reasons why it's good to choose 3x values is because it's a great way of checking to make sure that they're all collinear. So let's see, I'm going to pick -2, 0, and +2 because that seems like it would work pretty well. So let's see, if I sub in a -2 here, that's a -4 minus 1, so that's -5. If I sub in 0, 2 times 0 minus 1 is negative 1. And if I sub in a positive 2, this is 2 times 2 minus 1, that's 4 minus 1, that's 3. And you could do that in your calculator or in your head, whatever you're the most comfortable with. So if I graph that, we've got this one here, 0, negative 1, and 2, 3. So there's our line. There we go. Let's graph this next one. Let's see, those x values worked pretty well there, so I'm just going to pick those same x values. So if I sub in a negative 2 here, that's going to be negative 1/2 times negative 2 is 1, plus 3 is 4. If I sub in 0, that's negative 1/2 times 0 plus 3, so that's 3. And if I sub in a positive 2, this is negative 1 plus 3, that's 2. And again, you could always just type those into your calculator if you don't want to do that in your head. So let's plot those points. Negative 2, 4 is here. 0, 3, and 2, 2. So you can see they are collinear, which means we probably did a good job of evaluating our function, and there is our graph. So the question I have is, how are the attributes of the graph reflected in the equation of the function? Well, let's look at this graph and see what its slope is. Its slope is 2. And its y-intercept is negative 1. Can you see where that 2 and that negative 1 are showing up in the equation? Let's look at the next one. This is going down 1 over 2, down 1 over 2. So the slope is negative 1/2. And if we look at the y-intercept is 3. So look at that. Look at how the slope and the y-intercept show up right in the equation. So in other words, you don't need to use a table of values if you understand the parts of the equation. So when you're looking at an equation that is in slope-intercept form, you can go straight to graphing it without having to do a bunch of substitutions in a table. So this graph has a y-intercept of negative 4, and it has a slope of up to over 5. And we could repeat that pattern to get other points on the graph. I'm just going to go ahead and sketch it in there. Our next graph has a y-intercept of 8, and it has a slope of negative 3. So that's down 3 over 1, down 3 over 1. And again, you can repeat the pattern to kind of give yourself a lot of points to use to line up and get a nice graph. So this equation looks different, but it is still a line. How might we go about graphing it? Well, you could use a table of values, or you could solve for y. Get that y by itself and put it in that form that we recognize. So we might start by subtracting the 7x. So 2y is equal to negative 7x minus 10, and then divide by 2. And I'm going to divide both of these terms by 2 individually so that we can see the slope and the y-intercept. So the y-intercept is negative 5, and the slope is down 7 over 2. Now I can't exactly on this grid count down 7 over 2. So if that happens to you, you can do the slope reversed. I know down 7 over 2 means I would be ish here. So I'm going to go up 7, 1, 2, 3, 4, 5, 6, 7, and back 2. Just going to go through this point. It's a pretty steep line. Whoa, not very straight. Sorry, the end of that is pretty bad. Okay, close enough. So there's our lovely line. So now that we are an expert on slope-intercept form, let's try to write these equations. So our y-intercept is -2 on this one, and our slope is up 2/3. So our equation would be y equals 2/3 x minus 2. All right, on this one, our y-intercept is 5, and our slope, try to find those good points. Slope looks like it is going down 3/1. So -3. You don't have to do the over 1 because when we divide by 1, we just get -3. So our equation is y equals -3x plus 5. The slope is in front of the x plus the intercept. Okay, we've got two last lines here, a vertical and a horizontal. So our horizontal one has a y-intercept of 1, so that's y equals 1. Our vertical has an x-intercept of -4, so that's x equals -4. All right, that is it. So that was your quick review of lines. Let me or your teacher know if you have any questions. Thank you.